Okay, so let's go over some big takeaways for equilibrium and the graphing representations that we've been doing. So I highly recommend you pause the video now and try and do these true-false statements on your own, and then check your answers with me for each slide, rather than just let me show you the answers. But we'll take a second, pause, and we'll show you the answers. Okay, so a reaction at equilibrium is still reacting. That is true. I'll highlight true. All right, at equilibrium, the concentration of reactants and products is the same. That is false. The concentration of reactant products is not the same. It's that the concentration of reactants and products remains constant. So you can have, it's possible to have, it is possible to have more reactants and less products. We would just say that the equilibrium lies at the more with the reactants. It's reactant favored, for example, or you could have less reactants and more products. We would say that that is product favored. The equilibrium lies to the right, but it doesn't mean that the concentration is the same. At equilibrium, the concentration of reactants and products is no longer changing. That's the difference. Okay, so now let's look here. At equilibrium, the rate of the forward reaction is the same, slower, or faster than the reverse. At equilibrium, the rate of the forward and the reverse reaction are the same. It is if they are still reacting at the same rate as the forward and the reverse, but the concentration of reactants and products overall is not going to change. They're not that they're the same as each other, it's just that they're constant at equilibrium. So the reaction with more stable products would be, let's see, more stable products is going to be product favored. And the acid on that side, meaning the acid on the product side, if it is product favored, then it's going to have a higher pKa, because that would be the less acidic acid. So make sure that these statements are making sense to you, okay? Same thing here with the graphing side. I'm going to pause. I want you to spend time going through these statements yourself, saying true, false, higher, lower, endo, exo, whatever, and then we'll come together and talk about it. Okay, let's talk about it. So a reaction with more stable reactants than products would have the reactants placed where more stable reactants, then the reactants need to be lower than the products. This reaction would be considered to be the react. Let's draw a little graph for ourselves. Oops, get my pen back here. So we're saying that the reactants are more stable than the products. This would be positive delta H, endothermic, okay? Now, if we have more stable products than reactants, how would that look? Let's get my pen back. We have more stable products than reactants. We're looking at something like this. Here's our delta H. This is a negative delta H, exothermic. So let's review our graph, or our statements here. A reaction with more stable products than reactants would have reactants that are placed higher than the products, and this reaction would be exothermic. So if reading the statement doesn't make sense to you, that's okay. Draw yourself a little graph to represent that idea, and that might make more sense. The third thing here, the activation energy is the energy required to go from reactants to the what? The activation energy is from reactants to the transition state. That's this. Get my pen back here. I'll represent it in orange. Here's the transition state on this graph. So that would be the activation energy. Here's the transition state on this graph. So that would be the activation energy. You could also have an activation energy that went from products to transition state, but if that was the case, you would be going in the reverse order. So I'll draw that in, let's see, this light blue. If I went from products up to the transition state, this would be my activation energy for the reverse reaction. And then for the top one, if I went from products to transition state, this would be my activation energy for the reverse reaction. Okay, and the last statement here, the transition state is where the reaction is equilibrium. That is false. In fact, the transition state is the most reactive point in the reaction progress, and so that would certainly not be an equilibrium. Equilibrium is a state where the concentration of the products and reactants is remaining constant. It's not changing anymore. That doesn't mean that products and reactants have the same amount on each side. It just means that products have this concentration, reactants have this concentration, and it's no longer changing. But they are still converting between reactants and products at the same rate. So hopefully this clarifies some ideas for us.